We're going to talk about the number E. I know you're thinking to yourself, what? That's a letter, but it's actually a number, similar to pi. So our essential question is, what is the number E and how do you use it as the base of exponential functions? Well, I have a great website. It's called Math World. And I pulled up the number E. This Math World is from Wolfram. And I don't want us to write this all out, but I just wanted you to see that E is in fact an irrational number similar to pi, right? We'll usually approximate it as 2.7183. However, I wanted you to see that it in fact goes on and on and on without repeating pretty much forever. And we'll come back and we'll talk about this graph in a few minutes. So we're going to write an approximation of E. 2.71828 1828. Noting that it goes on, it continues on, and it does not repeat, even though originally it does look like it repeats. And we'll approximate that usually to be about 2.7183. Now, the cool thing about this number, people have come up with a lot of ways to remember this number. And somebody once came up with calling it the Andrew Jackson number. And the reason they did that is because Andrew Jackson, who was a U.S. president, he served 2 terms. He was the 7th president. And he was elected in the year 1828. So if you know about Andrew Jackson, maybe this could be a way that you remember this number. Otherwise, the rest of us are just going to remember it as 2.7183. All right, so as you can tell then, or as we've talked about, since it's like pi, we call that an irrational number. Since it does not repeat and it does not end. The person that actually came up with this number, or that is credited with coming up with this number, is called Euler. Now, his name is actually spelt with an E. Okay, so we call this Euler's number because the man named Leonhard Euler, who lived from 1707 to 1783, is the one that's credited with coming up with the number E. Now, we call this the natural base. The number E shows up a lot in nature, and it shows up a lot in and also in logarithms, which we're going to end up getting to. But there's going to be like a logarithm that has a base of 10, and then there's going to be a logarithm that has a base of E. And we're going to use the natural logarithm to deal with the natural base of E. Okay, so that's why this is called the natural base, because it goes with the natural logarithm. All right, I'm going to define it for you. Now, in order to define this, to give you the actual definition, I'm going to have to use a little bit of calculus. It's not that big of a deal, and I'll show you graphically what it means. But basically, the definition of E, it says that E is equal to this limit as n approaches infinity. So as n gets really, really big, of the quantity 1 plus 1 over n to the nth power. And if you actually put this into your calculator, so we're going to do that in a second here, but if you put this into your calculator, you will see a graph that as n or as x gets really, really large, this thing approaches approximately 2.7183, and so on. Okay? So I'm going to do that right now. So in our calculators, we are going to actually put this value in, and we're going to graph it. We just got to turn it on first. So I pretty much already have it. Now I'm using x instead of n because we don't have an n variable in our graphing calculators. And I'm going to raise it. Let's see how come this is. Raise it to the x power. And my window I have the x value pretty big, but the x min I have very small to -1. And on the y scale, I've only set my y maximum to 10, my y minimum to -1. And I'm going to graph it, which I can see it's kind of flattening off. Okay, and it's hard for me on this graphing calculator to tell exactly what number it's approaching. But what we care about in this form or in this equation is the limit as n, or in our case x, gets really, really large, goes to infinity. What number is it approaching? And I can show you, maybe instead of using just the graph to show you that, I'm going to use the table, okay? So I'm going to do, let's see, I'm going to set my table. I'm going to set it at something really large. Maybe, why don't I set it at 100? And then I'm going to change my table. Maybe I'll go up by like 20s. Okay, and then I'm going to look at my table. And what I see is, at 100, it's at 2.70. Let's see. By the time I get to 220, I'm down to 2.71. Okay, but I can keep going. 2.714, 2.715, and so on. Maybe let's set this to a really big number. Let's set it to, how about 1 million? Okay, and why don't I change my table by, how about hundreds? And let's look at the table now. So starting at 1 million, that's really 1 times 10 to the 6th power. Look at this, I'm at 2.7183. Okay, if I want a more exact number, it's going to be right here. So I'm getting closer and closer and closer, right? And as this number just keeps getting bigger and bigger and bigger, I'm getting closer and closer and closer to that approximation of what pi actually is, or not pi, I'm sorry, what e actually is. Okay, so that's what a limit means. The limit is saying as that value of x gets really large, I am approaching some output. And that output that we happen to be approaching with e is about 2.718 or 2.7183. Okay, so that's e, that's the definition of e, and that is an introduction to limits for you. All right, I've got more stuff to go over with you. So I'll put that away for a little while. Oh, I do actually, let's pull that calculator back up because I do want to show you that there is an E button on your calculator. So I'm going to get out of my table mode, and here I just did e to the 1st power. So I'll show you, and it gave me an approximation, right? E to the x power is right above the ln button, and this is actually the natural log button, ln, and then e to the x is right above it. So anytime you want to use e to the x, you just hit that. If I wanted e squared, there it is. Okay, so that's your e button. So let's do some examples, realizing that working with e is just like working with any other variable out there, except for that e actually has a value to it, okay? Whereas other variables, maybe we don't know what their value is. Our first example, we're just going to simplify. Okay, so you'll be given an expression, like for example, e squared times e to the 6th. Well, I'm going to treat this just like x, right? So I've got like bases. I'm going to add the exponents. How about e to the -2 times 3 e to the 7x? Well, first of all, looking at the coefficients, that's 3 times 1. That'll give me 3. And then I'm going to look at my e's. They're like bases, so I'm just going to add these, really? So now the problem is that my exponents are not like terms. So this would really be like 7x minus 2 or -2 plus 7x. I'm going to write it 7x minus 2. Oops, e to the 7x minus 2. Let's make that look a little bit better. Okay, so nothing new here. The only thing that's new is that you're learning about e being some number. Okay, let's see. How about the square root of 36e to the 4x? Okay, well, I can break this up. I can think of this as like the square root of 36, which I know that one, times, how about instead of writing the square root of e to the 4 to the x, how about if I say e to the 4x raised to the 1/2 power, right? Because that's exactly the same thing as writing the square root, 1/2 power. So this is going to give me a 36. Now, e to the 4x to the 1/2 power is really e, well, I take the 4x and I multiply it by 1/2, right? So that's really going to give me e to the 2x. Right? So these aren't too complicated. All right, let's do one more. What if I have 12e to the 4th power over, how about 36e to the -2? Okay, well, I'm going to start out with my coefficients. Those can reduce, right? This is 1 and this is 3. Okay, so I'm going to be left with a 1 on the top and a 3 on the bottom. Then you've got e to the 4th and e to the -2 being divided. So like bases, if you're dividing, that means that I subtract these. So this is really e to the 4th minus a -2. Right? So think about that. 4 minus a -2 is really going to give me e to the 6th. Okay, let's put this into our calculator just so that we can actually get a value and make sure that we can use our calculators, okay? So I'm going to evaluate this and I'll round to, I don't know, the nearest hundredth, okay? So I'm going to do e to the 6th, and then I'm going to go down and I'm going to divide that by 3. And I'm getting approximately 134.48. You know, there will be times where it'll say round to the nearest hundredth, and so this will be the way that you would give your answer. Other times, you're going to want to leave it in this form, okay? It just depends. All right, so we can also graph these. So I'm going to go onto the back of my paper here. And it's just like graphing any other function, any other exponential function, okay? So we are going to graph natural base functions. Okay, so I'm going to start with, I'll start with f of x equals e to the x power. Well, let's think about this. My base is 2.718 approximately, right? So my base, if my base is bigger than 1, this is going to be an exponential growth function. So I know from exponential growth functions that I had an asymptote at the x-axis, and that this thing looked something like this, right? So let's think about that. Does it still look like that? Well, if I plugged in 0 here, e to the 0 power is 1. So I definitely have 1 on here, okay? If I plug 1 in, that's going to give me approximately 2.718, right? So I'm going to go up to 2.178, not 2.718, 2.178. So I'm going to go up a little bit above 2, approximately there. And if I went to -1, well, that would really be like, let's see, I'll make an XY chart here. At -1, that would be e to the -1, which is the same thing as 1 over e, which is the same thing as approximately 1.21718, right? Okay, So if that's the case, that's really approximately 1/2. So at -1, I'm about 1/2. So it's not too far off. The only difference is, it really just depends on what your base is, right? And here my base happens to be 2.178. So it's basically an exponential growth function. However, there's always that caveat of when you have that negative exponent. Well, what does that negative exponent do? That negative exponent, I can rewrite this. Instead of having an e to the negative x, I could rewrite it as 1 over e to the x, right? So now I have 1 over 2.178 to the x power. So is this an exponential growth or an exponential decay? This one, because my base is in between 0 and 1, is going to be an exponential decay. No shifts, though. Don't worry, there will be some shifts in your homework. But right now, we're just getting a general idea of what these look like. So I'm still going to have 0, 1. This time, though, if I put 1 in, I'm going to get the 1/2, or approximately 1/2. And if I put -1 in, right, -1 would flip this back over, okay, and I'd be up to 2.1718. So approximately here. Okay, so this one's going to be a decay. Right? And so there's really nothing new here. We're doing the exact same thing we've been doing in the past couple of sections with exponential growth and exponential decay. So let's do a couple of these graphs. So example 2, we're going to graph the function. So the first one we'll do is y equals 2 times e to the x minus 2. Okay, well, let's think about what components I have here. Okay, I have a 2. That's like my a. That's my stretch factor, right? So this thing's going to stretch it vertically. And what's that minus 2 going to do? Well, that minus 2 is going to move it down 2, right? So we're going to have a vertical, or I should say shift down. I should have just written that, but we'll do a vertical shift down 2. Okay, so let's go ahead and graph this. Otherwise, it's the exact same thing. However, remember there's that asymptote. That's the x-axis. So because I have this vertical shift down 2, that means I'm going down 2. My asymptote is now down to -2. So again, I know right away that I've got this vertical shift down of my asymptote, and it went down to -2. So that's my asymptote. Okay, now, I know that my original parent graph would have looked something like this. But I also know now that everything has been shifted down too. So I'm thinking, okay, it's going to look something like this instead. But there's that stretch factor of a 2. So I also need to take that into consideration. So I'm going to plug in some numbers. Starting with an easy one, let me go ahead and plug in x equals 0. So when I do that, e raised to the 0 is 1 times 2. Well, that's just going to give me 2 minus 2. That gives me 0. So really, remember this thing, that stretch factor, it's stretching it vertically. So really what I thought should have been at -1 is actually going to be up here at y equals 0. Which is important. That's important that you go ahead and you plug in a couple of extra numbers here. Okay, now the hard part about this is if you weren't allowed to use a calculator, there wouldn't be much more that you could do. Okay, but let's go ahead and we'll use a calculator on this one. So why don't I go ahead and do 1 and -1 just to get an idea, and then we won't be so picky from now on. Okay, so if I plug in 1, well, that's 2 times, let's see, let me get my calculator. So I'll have 2 times e to the first, and then from there, I'll subtract 1, or sorry, 2. Yes. So I'm getting 3.43. And then at -1, so I'll do the same thing. Now I can go, let's see, will this let me do it? Yep, I can go back up here. Some of your calculators will let you do that, and others you have to retype it in. I'm just going to go here and I'm going to insert a negative. Oops, it doesn't like it because I probably put the wrong thing. So it doesn't like that because I put a minus sign, I bet, not a negative. There it is. There's the negative. Always, whenever you make an error, use go to. Don't hit quit, okay? And I'm going to press enter. And that's negative 1.26. Okay, so now I can graph that. So at 1, I'm approximately 3.4. So let's say up there. And at -1, I'm down to negative 1.2. So approximately here. And I already know what this thing's going to look like. It's going to approach that asymptote but not touch it. And that stretch factor of 2 really stretched it out a bit. Okay, I'm going to do another example, but before I do that, I want to go back to this graph right here, or these 2 graphs. And I know I've touched on this before, and I just want to reiterate again that, you know, when we have a negative in front of our function, so if I were to put a negative in front of e to the x, that would be a reflection in the x-axis, right? So this would actually end up being reflected or symmetrical in the x-axis. And when I put a negative in front of my input, though, so when I put a negative in front of x, that actually, what it does is it just takes this graph, and now it makes it a reflection in the y-axis. And that's going to be true for any graph. So if you put a negative with your input, you now have a reflection in the y-axis. Whereas if you put a negative in front of the function, you reflect it in the x-axis. Okay, so moving on, let's do another example with that in mind. So this you should be saying to yourself, well, I know that my base is e. So if my base is e, that means that it's bigger than 1. So it's going to be an exponential growth. However, you should then be saying to yourself one of 2 things. Based on what I just said, you could say to yourself, well, but my input is negative. So that tells me that it's going to be a reflection in this y-axis. Or the other thing you could say to yourself is, okay, well, I know that if I have a negative exponent, I need to do the reciprocal of my base to make this positive, right? So I could rewrite this as 1 over e to the 2x. Okay, I just took the reciprocal of the base. Well, now 1 over e, that's like 1 over 2, right? So now my base is actually a fraction. So I know that this is going to be a decay. Okay, and then just coming up with a couple of points. Let's see, I don't have any shifts happening, right? So coming up with a couple of points, I know that, let's see, 0, plug in 0, I get 1. Okay, and then I could do a couple more points. So plugging in, let's see, positive 1. I'd get 1 over e squared. Okay, so using my calculator, I'll get a better idea. It's going to be about 1/4, but I can go back to my calculator. So let's see. So that's not good. So about 0.14. Okay. And then if I go to the -1, well, if I do that, that's going to make this a -2 now, right? So now that's just going to be e squared, which I think, have we done e squared? No. It's about 7.3. So that's going to be way up here somewhere. So the last thing we need to talk about is compound interest. And we've already talked about how great compound interest is. Sorry. So the fact that compound interest gives you interest on interest that you're already earning is pretty cool. And so we had one compound interest. So this is one that we've already done. I'm going to put recall compound interest formula. This is where you knew it was compounding a certain amount of times per year. The number of times per year was the n. So if it was monthly, you put 12 in here. If it was quarterly, maybe you put 4 in here. If it was, semi-annually, you'd put 2 for n number of times. Okay, now, an even better compound interest would be if it was continuously compounding. So if you invest money and right away you earn interest on that. Now, of course, that's going to be like fractions of pennies, and then you're going to earn interest on that, which is still fractions of pennies. But over the long term, that's going to give you more money. So continuously compounding has the E in it. And the way that I remember this is I call it PERT. I don't know if they still have PERT shampoo, but PERT used to be a shampoo. And so it's basically the principal times E raised to the rate times time. That'll give you your amount. Okay, so we're going to use, anytime that you invest, this is the best kind of interest to be getting. Anytime you borrow money, this is not the best kind of interest to be paying. Okay, because this is, again, it's continuously compounding. So it's taking whatever interest you just got paid, and now it's giving you interest on that. And then it's giving you interest on that, and so on. Okay, and of course, the more money you invest, the higher the amount of interest you'll be getting. So we're going to do one more example here dealing with compound interest. So we're going to find the value of $3,000 invested at 2.5%. If it is compounded continuously for 5 years. All right, well, the initial investment, or the principal, is $3,000. My interest rate that I'm getting is 2.5, or I'm going to want to turn that into a decimal. And I know my time. So I'm going to go ahead and write out my formula, and then I'll just plug it into the calculator. So the amount that I'm going to get after whatever amount of time will be my principal, which is 3,000, times E. And then E is raised to the rate, but remember, rate needs to be in decimal form. So that needs to be 0.025 times time, which is 5. And I'm just going to plug this into my calculator. Let's see, I'll try and move my calculator this time so you guys can see better. All right. If I wanted to graph this, I could put it into the graphing section, but not really necessary. Oops. All right, so in approximately 5 years, I've made about $400 on this investment. So $3,399, and how about 45 cents? Pretty easy formula, and pretty easy one to even remember. Again, PERT is continuous compounding, and if you're compounding a certain amount of times a year, then you're going to use this one. Either way, I'd have these all on your note card for a test.